Yep. All right, here we go. Let's rock and roll. Do this optimization problem here. It says find the dimensions of the rectangle with largest area that can be inscribed into curve y equals 4 minus x squared between -2 to 2. And it says the top corners of the rectangle are going to lie on the curve. All right. So I did all the work here for you so we can kind of save time. So obviously the first thing I want to do is write down what it is we're trying to find, right? So we want to find largest area. So I want to write down max area. Always write down what you want to optimize, right? Put things into context. All right, so this is my first thing. I got that down. Now I have to draw the picture. So we know what a parabola looks like. Y equals 4 minus x squared. It's going to be concave down, right? It's going to have a y-intercept at 4. And if you set 4 minus x squared equals 0, you'd get x-intercepts at -2 and 2. So that should go without saying. All right, so that little red curve there is my best sketch at a parabola. And what we want to do now is inscribe a rectangle under this little arch here. So I drew through three rectangles. You really only need to draw one, but I drew three. All right, so the first one you can see here is this little gray rectangle, right? This flat rectangle here has a small height, relatively speaking. And the top 2 points are here and here. So that could possibly be a rectangle that's inscribed. You can see it doesn't have much area. Then I drew another rectangle, this tall, narrow rectangle, right, where the top 2 points are touching here and here. And again, it doesn't look like it would have much area. So those are two possibilities of my answer here, but it probably seems reasonable that the area or the rectangle with the most area is going to be somewhere between those two, right? And that's where I drew this blue one. And quite honestly, that'd probably be the only one that I draw. So now I like to label the point, right? This top right vertex that's touching the curve, right? It's an unknown point, so it's an x comma y. So I could have labeled it xy. Instead, I labeled it x comma what y is, which is 4 minus x squared. All right, so now the picture's drawn. So if you want to maximize area, you have to get an area function, right? So you might like knee-jerk reaction say, okay, area equals x times y, but that would not give you the area of this rectangle, right? So think about it. How do you get to this point from the origin? You go over x and up y. That's what this little x and y labeling is here, right? And that happens from the origin. So this distance is x, not the base of the rectangle. Right? So what would the base be? And you can see I labeled it. It would be 2x, right? Because 4 minus x squared is symmetric to the y-axis. It's an even function. So if this is x, this is x. So the base is actually 2x. The height would be y, right? It's the y value on that curve, right? Because it says it lies on the curve, that top vertex, okay? So the area is going to be 2x times y. But just like we said in class, this is no good. You have a function in terms of two variables, and you want a function in terms of one variable. So you'd say, oh, if only I knew what y is. Well, you know what y is, right? Y is 4 minus x squared. So I can go ahead and chuck 4 minus x squared in there. And that would be my area function. So right now it's written as a product, and there's nothing wrong with that, but eventually I know I have to take the derivative. So I'm going to avoid using the product rule. I'm going to distribute here. So if I distribute 2x times 4 is 8x, 2x times x squared is going to be minus 2x cubed, right? So this is good. So now, how do I get this stuff in blue? What is the stuff in blue? Stuff in blue is your interval, right? What are the constraints on your variable? What are the constraints on x? What can x be? Well, it should be obvious that x can't be bigger than 2, because if x is bigger than 2, I would no longer be under the rectangle, right? I'm not going to be scribed inside, right? So the biggest x can be would be 2. The smallest, I guess, is a little weird. You might say -2, but you kind of repeat rectangles if you go from -2 to 2, right? Because of this whole symmetry thing. So really the smallest I'm going to say x could be is 0. And if you think about it, when x is 0, I get this little orange thin rectangle, right? It's not really a rectangle, it's a line. It's what we call a degenerate rectangle with an area of 0. And when x is 2, that stretches me all the way over here, then I would get this flat line, which is a flat degenerate rectangle, which would have an area of 0. Now, if that goes against all your moral beliefs and you're like, no, you can't have a degenerate rectangle, the interval needs to be open, then knock yourself out and open the interval. That's fine. But just understand then you'd want to take limits and show limits here. And if you think about it, if you open the interval and say, all right, the x can approach 2, that's fine. So as x approaches 2, then this flat rectangle is what we're approaching. So the area of that is approaching 0, which is the same thing as if we just plug to it. And this similar would be true if I said as x approaches 0, the area of that thin rectangle is going to also approach 0. So whatever floats your boat. I like doing it this way because if you have a continuous function on the closed interval, you can mention the extreme value theorem. And if you remember, the extreme value theorem guarantees that if your function is continuous and you have a closed interval, then the extreme value theorem applies, and it guarantees that you'll have an absolute max and a min. And they will occur at candidates. And candidates are critical points and endpoints. So let's get the critical points. So I take the derivative right here. I set it equal to 0. I happen to factor a 2 out. I add the 3x squared over, divide by 3. I plus or minus square root to solve for x. I realize the negative I don't care about because it's not in my interval. So I get 2 over radical 3, which you know what? I'm going to figure out what that is as a decimal. So 2 divided by radical 3. I chuck that in my calculator. I'm going to get 1.154 ... Okay? So that's my only critical point in this interval. So we say since A is continuous on the closed interval, the extreme value theorem applies. That's really the good way of saying what we're about to do, right? So now once I say that, I can say, okay, let's test all the candidates. So here are your endpoints. Here's your critical point. Now, what's the best way to test these? If you're allowed to use your calculator, it would be to use your calculator, right? So what I did over here is in y equals, I actually had the parabola, and then I had the function that I'm trying to optimize, right? This is the area function. So now if I wanted to test these values, it's pretty simple, right? Just do function notation. Vars, y vars function, and since it's in y2 for me, I'm going to do y2 of 0, okay? And you get 0, and you knew you were going to get 0 because that's that flat rectangle, right? And or you could just plug it in yourself, right? Because those aren't really too difficult to plug in. And it'd be the same thing with the other value, right? If you chucked 2 in, you could do that without a calculator. You're going to get 0. The one maybe you didn't want to do without a calculator is what you get when you plug in the critical point. So now the critical point was 2 over radical 3. So right, if I do that, 2 divided by, let's get rid of this, 2 divided by radical 3, right? I'm just kind of showing this for future reference. And get it? That's the decimal. Probably not a bad idea if you store that. So I'm going to store that in, say, the locker location A, right? The variable A. So now it's stored in A. So now if I ever want to use that value, right, with lots of accuracy, I can use A instead of actually having to type in 2 over radical 3 every time. So likewise, I can go vars, y vars function, y2, right? And now I want to go ahead and right? Sorry about the little noise that you heard. So I chuck in A here, I'm going to get that, right? And that's what you can see I wrote down right here, which is pretty good, okay? So you're like, all right, so let's answer the question. So obviously this is the max, right? 6 is bigger than 0. So we have a max area of about 6 square units. Now we have to answer the question. The question said find the dimensions of the rectangle. So remember, the dimensions are 2x by y. So obviously this dimension here is going to be 2x. So 2 times 2 over radical 3, which I wrote as 4 over radical 3. And then by what's the y dimension? Well, the y dimension would be whatever 4 minus x squared is when x is 2 over radical 3. So that would be 4 minus basically 4/3, right? We can probably figure that out. In fact, why don't we do that, right? I could do it over here. I'll do it right over here. So we have 4 minus 2 over radical 3 squared. So that's going to be 4 minus 4 over 3. I'd rather think of 4 as 12 over 3. 12 over 3 minus 4 over 3 is 8 over 3. You're going to get 4 over radical 3 by 8/3, which obviously is 2.666. Repeating, I had the decimal in there before. So I just wanted to keep everything clean, right? If I wanted to do the decimals, I could say, this times 2, right? I could do 2a in my calculator, write down the decimal by 2.6, and that would be fine too. But these are the dimensions, and that is the question answered. All right, so pretty standard classical max area inscribed type of problem for calculus, all right? That's one down. We got one more to go.